So hello everyone. Today we are very happy to have Dario Cordero-Erausquin from Sorbonne University, and he's going to talk about the convexity, duality, and heat diffusion.
Thank you very much, Juan, for the invitation. Here where I am in France, it's a vacation and 8 p.m. So certainly not the time to do anything sophisticated. I really plan to give all details, all proofs, and also recall some classical things. But anyway, please stop me because I really intend to give all details of the topic. Uh, the plan of the talk is as follows. I will first start by the motivation for our results, and it comes from convex geometry, from the Blaschke-Santalo inequality. Then I plan to recall some basic things about heat semigroup and log concavity. And the main result is how this interacts with the Legendre transform for convex function. I will then go back to the proof of the Blaschke-Santalo inequality. And if I have time, I want to discuss the non-even case because there is a symmetry assumption, and then also discuss similar inequalities for the Laplace transform. Okay, so let me start with the Blaschke-Santalo inequality. So I will be working on the Euclidean space, Rn, with unit ball that I will denote B2n. And given a convex body, you can define its polar as follows. So it's the set of all vectors such that for all x, here is missing for all x in K, you have x dot y smaller than 1. Okay, so for all x in K, you must have this smaller than 1. And you have every convex set is a polar by the Hahn-Banach theorem. And so the double polar will be the convex set itself. And the Euclidean ball is, of course, is a fixed point for this transform. So when 0 is in the interior of the convex body, the polar will also be a convex body. The origin plays a special role here in this transform. So for the moment, I will assume that K is a symmetric convex set with respect to the origin. And then you can define what's called the volume product, which is the product of the volume of K. Here, the volume is just the Lebesgue measure on Rn. So the volume of K times the volume of the polar body. Okay. And you can note that this has a nice property that it is a linear invariant in the sense that if you apply an invertible linear map, it does not change. So you can ask somehow what is the maximum or the minimum of this quantity over all symmetric convex body. And today we will be interested in the maximum of this quantity. And there is a famous result that says that this is maximal for the Euclidean ball for any symmetric convex body. So I have not checked the original proof by Blaschke-Santalo. There is some differential geometry, but really somehow the modern proof appeared in the 80s, first by Jean Saint-Raymond, and then there is a general result by Mathieu Meyer and Alain Pajor, who proved this had this very nice observation that the volume product increases by Steiner symmetrization. And so, of course, if you perform a sequence of Steiner symmetrization, you will arrive somehow to the Euclidean ball. Okay, so we will be interested in functional versions of this inequality, and the the functional analog of a convex set is a log concave function. So there are various reasons for that. Maybe we will see some of them. So a log concave function is just a function of the form exponential minus phi, where phi is a convex function. You can define the Legendre transform, which is somehow the analog, which gives you the duality for the convex functions, which has the supremum over all x of x dot z minus phi of x. And then Yes, sorry. I wanted to mention that some authors prefers to work directly with the log concave function. So in particular, you can define what's called the polar of the log concave function, which is exactly the log concave function, which is defined by the exponential minus the Legendre transform. And here you have a formula. But somehow I prefer to work with convex function, at least today. So I will keep this notation, phi star for the Legendre transform. And so you can define the volume product of the log concave function exponential minus phi to be the product of the integral of exponential minus phi times the integral of the exponential of minus phi star. And you can observe again that you have some linear invariance, so that this quantity is invariant if you perform a linear transform here and if you add a constant. Okay. So the Keith Ball proved in his PhD that it is also the case that you have an inequality for the functional volume product, and it is maximized by Gaussians. Okay, so and for a Gaussian, when I say by the Gaussian, you can take, of course, any Gaussian because we prove it has some linear invariance. And here the function, the analog of the symmetry is that the convex function is even. So Keith Ball did use this inequality from the Blaschke-Santalo inequality. There is a nice trick. You apply the Blaschke-Santalo inequality to the sublevel sets, but then you must do something more, and you have some kind of Brun-Minkowski inequality on the sublevel sets, and you derive this functional inequality. This you can recover the geometric form by applying this functional form to the gauge of the convex function k to the square, because for any convex function, this is just a multiple of the volume of the convex body. And you can observe, it's a very simple computation, that the Legendre transform of the gauge to the square divided by 2 is the gauge of the polar to the square divided by 2. So, and of course, again here, maybe I should have said it before, the Euclidean ball was a fixed point for the polar. Here, if you look at the Legendre transform, the Euclidean norm to the square over 2 is a fixed point for the Legendre transform. So again, this tells you that somehow this is maximal for the fixed point of the Legendre transform. Okay. So there are many proofs of this inequality, and there are several proofs by Joseph Lehec, which do not use the geometric form, but nevertheless they all requires very strong geometric arguments somehow. And some natural question is to have like some streamlined geometric approach to this inequality. So by this, so I want to prove this inequality. And one of the things I would like to have, because this appears in other topics of log concavity, one would be to have like some convexity along some path in the set of convex function that will join the function to its polar, passing through somehow the quadratic function, and you will have some convexity along this path. So this is actually possible if you work on Cn, because it's very strongly connected to complex interpolation and to homogeneous complex Monge-Ampère equation. So you can do this in this complex setting. I don't know of a similar way to do it on Rn in general. And another possible path, if you are familiar with semigroup, is to prove that some quantity increases along some semigroup, and you prove some monotony along some path. So this is the kind of two things we would like to have. And actually, for the second, this was very recently solved by Nakamura and Tsuji, because they indeed obtained that the volume product increases when the log concave function exponential minus phi evolves along the heat semigroup. So in some sense, you could say this answers the point two, but not completely. One reason is that the argument in the paper by Nakamura and Tsuji is a bit indirect in the sense that they don't prove directly this, they prove some analogous result which involves the Laplace transform in place of the Legendre transform, and then they pass to the limit and obtain this result. So somehow our goal is simply here to try to understand if there is a direct approach to this monotony along the heat semigroup. So let me recall some definitions. So I will call PT the heat semigroup. So it's just convolution with a Gaussian here with variance 2t. And this solves the heat equation when u is as a function of t and x. So the problem with heat somehow is that, well, of course, it tends to a very flat Gaussian. So you may want to somehow renormalize the heat flow so that, for instance, it remains with finite variance. And so this leads to the Fokker-Planck semigroup. So Fokker-Planck here, for me, it's just a renormalization of the heat semigroup. And it evolves according to this equation, Laplacian V plus divergence of xv. And somehow the advantages of this semigroup Qt is that it connects f exactly to a Gaussian at infinity. So a Gaussian which has some weight, which is the integral of f. And this has to be because both the heat semigroup and the Fokker-Planck semigroup preserve mass. Okay, so we will use this semigroup. And the first thing is that since we want to stay in the set of log concave functions, you may ask if whether this semigroup preserves log concavity, and this is a very classical result that indeed, if f is log concave, then it remains log concave at all time when f evolves along the heat of the Fokker-Planck semigroup. So you see here, there are several dates. And the first date, I learned it very recently in a paper by Boas Klartag, who mentioned that 3 Russian authors seem to have proved this result. So I don't know, Boas is maybe connected here. He can give it more reference. I must admit I did not check this paper. So, okay. Sometimes this is attributed to Prekoppa, which is the second date here, because indeed, as we will see, it follows from a general result of Prekoppa. And here the third date is a paper by Braskamp and Lieb. Sorry, the date is wrong. I think it's 76. Which also contains this result, but it also contains more information that will prove crucial for us later. So as I said, this is a very particular result of the fact that log concavity is preserved when you take marginals. So if you have a log concave function of n plus m variables and you integrate m of them, the function that you obtain remains log concave. And of course, since if f is log concave, of course the heat kernel is log concave. So as a function of x and y, this function is log concave. And so you can apply directly this result. But here today, I would like just to give a proof of this result, a direct proof of this theorem just by computing by checking directly that this function is log concave. So of course, I have to check it at all time, but without loss of generality. You have the semigroup property, so you can take t to be 1/2 if you want. And so here I have my, so what I want to prove is that I have my log concave function here, exponential minus phi. I take the heat semigroup, and I want to prove that it remains log concave. So I take minus the log. I want to prove that this function phi here is convex. And to do so, convexity is just a one-dimensional property. So I will fix a vector y0. I will fix some direction θ0, and I will consider the one-dimensional function alpha, which is phi along this affine line. Okay. And what I want to prove is that this function is convex, so I will compute its second derivative at 0, and I will use dots just to not to confuse the derivatives in the space and the derivative in the variable s. Okay. So here I recall the definition of alpha. I have this my log concave function, here the heat kernel. Okay, so I compute the first derivative. So the first derivative, you have θ0 dot x minus y0 minus s θ0 times the same function here. So I will give a name to this, which is, this gives you a probability density. So I will give a name to this probability density, and I will compute one more derivative in s at 0. So what happens here, so I will call mu0, as I told you, just this probability density here, and I compute one more derivative in S. So when I take the derivative here, it gives me θ0, θ0. If the signs are not wrong, this is just 1, because it's a probability density. And then here, what I have is, what I have left is two terms. And if you compute it correctly, it's exactly the variance of as a function of x of the function x dot θ0. Okay, and so the question is whether this variance is non-negative, right? So we must use some property of this inequality, and the idea that appears in the paper by Braskamp and Lieb is that indeed you have some kind of spectral inequality that proved to be very important in various fields, that tells you that if you have a log concave probability density, so probability density with given by exponential minus v, with v smooth convex function with finite integral, and you call mu v the normalized measure just to have a probability density, then what you have is that for any smooth function u, the variance is bounded above by, so this, you view this as a quadratic form on the space of vectors. So it's the Hessian of v at point x. You take its inverse and you apply it at grad u, and then you dot with grad u. Okay. So in our case, what is the function v that comes from the heat semi-group, where v was just our function phi. Sorry, there is different fonts for phi, but it's always the same convex function. And then this quadratic term. So in particular, if you look at the Hessian of v is the Hessian of phi plus the identity, so it's greater than the identity. And in particular, you have this Poincaré inequality, so that the variance is smaller than the gradient u square. And now we just apply it to our linear function. So on the right-hand side, you will have 1, and on the left-hand side, you will have the variance of this linear function, and this is exactly what we wanted. We wanted that this 1 minus the variance of a linear function to be positive, non-negative. Okay, so this finished the proof of this of the preservation of log concavity. So this proof, of course, is essentially the argument of Braskamp-Lieb, and actually, I should say that using a similar result, one can prove Prekoppa theorem, although this is not exactly the way it's done in the paper by Braskamp-Lieb, because it's the other way around. No, sorry. Actually, what I wanted to say is that this result is really equivalent to Prekoppa theorem, but in the paper by Braskamp-Lieb, indeed, they deduce Prekoppa theorem using this the inequality, more or less generalizing the argument I just gave. So very quickly, the argument in the paper by Braskamp and Lieb is on, there is some induction. It's a very clever but not so simple argument. And it turns out that in a different setting, there was a proof of a similar inequality by Hermander in his study of the D-bar equation. And the proof you can give somehow is as follows. You introduce the operator L, which is the gradient associated to your density V, exponential minus V. And what you have is a Bochner formula. So you have that the L square, you have this formula is equal to the Hessian of V grad U plus the Hilbert-Schmidt norm of, sorry, here it was F. LF squared Hessian V grad F plus the Hilbert-Schmidt norm of F, of the Hessian of F. This is just integration by parts somehow. And of course, this is bigger if you just drop this Hilbert-Schmidt norm. You end up only with the Hessian of V grad U, and somehow this is just the dual, right, in L2 with respect to this operator L. This is just somehow the dual form of this inequality. Okay, so this is somehow classical results. So let us go back to our problem. I recall that what we want is to prove that the volume product increases along Fokker-Planck, because in Fokker-Planck you see that you really tend to a Gaussian. But as we said, you have this linear invariance for the volume product, right? So of course it is the same either for Fokker-Planck or for the heat flow. So I will rather use the heat flow just for simplicity, but the same you can do the same with the Fokker-Planck flow. So I call phi index t minus the log of pt of exponential minus phi. And so we just checked that this phi t is indeed a convex function. And I will use the notation psi t for the Legendre transform of phi t. Okay, so what we want to study, so it's the volume product of pt of exponential minus phi. So pt of exponential minus phi, by definition, this is exponential minus phi t times the integral of exponential minus the polar of phi t that I call psi t. And of course, as I said, the heat flow preserves the mass, so it preserves the integral here. So the only thing that really depends on t is this integral. So what we want to prove is that the integral of exponential minus psi t increases in time. Yeah. So the evolution of phi t is very simple, because exponential minus phi t follows the heat flow. So you have that dt phi t verifies this Jacobi type Bellman-Jacobi type equation, which is Laplacian of phi t minus grad phi t square. This is just a direct computation. And somehow our main result is just to find a formula for the evolution of the Legendre transform of phi t. So here, it's not really a theorem, but I have only one environment in my beamer, which is theorem, but this is really a fact or a lemma. But surprisingly enough, at least to my knowledge, this was not noted before. So you are given some convex function. As before, exponential minus phi t is pt of exponential minus phi. Phi t is convex. You call psi t the Legendre transform. Then psi t evolves according to some very simple equation, which is the derivative in time of psi t at point z. This is z square minus the trace of some matrix of some operator, which is the inverse of the Hessian of psi t. Okay, so this is the equation for psi t. If there are any questions, please do not hesitate to. Okay. So now we have an equation. We have this equation. So I will first give you the proof of this result. Somehow by waving hands, you will see why. So the first thing is that there is a somehow a general property when you perturb convex function. So this relation that I've written here has nothing to do with the heat flow. It's just if you perturb phi t, the convex function, you want to see how it perturbs psi t, and the relation is here. The perturbation of psi t is minus t phi t at grad phi psi t. This is probably some kind of general property of convex envelopes. So let me give you a proof, a very quick proof of this result. So here I record the definition of the Legendre transform. I will fix a point z naught and t naught, and I will assume that this supremum is attained at the point x, and this point x verifies x naught verifies this property that grad phi at t naught x naught is z naught. Okay. So what I really want to compute is psi at, I want to compute the derivative in time. So I will do psi t naught plus epsilon for some small epsilon, and I'm looking at this at the same point z naught. So here it's the same definition as before, but except the point x, I call the point x naught plus epsilon y, where y is generic. So I haven't really done anything here. It's just another way of writing a generic point in Rn. But of course, the idea here is that when epsilon is small, this supremum will be obtained at some y, which will be close to x. Sorry, the supremum will be attained at a point which is close to the point x naught. So it makes sense to write it as x naught plus epsilon y, and you expect y to remain somehow maybe bounded or something like this. So if you look, if you do some Taylor expansion here, you will have the zero order term, which is phi naught x naught with z naught x naught, and this is by definition the psi t naught z naught. And then you have the rest. So what is the rest? You have an epsilon z0 y here. And here you have the term in epsilon. So it comes from two parts. First part is minus epsilon, the derivative in time at t naught, at the point x naught, minus epsilon, the derivative in space here of, so it will give you the grad phi t naught at point x naught dot y. And here is where I am a bit cheating, because this is what I just said. I assume that somehow y can remain bounded. So I assume that this capital O of epsilon square is somehow uniform in y. For this, you have to make some assumptions. And the assumption we make is that we have the convex function is superlinear, is at infinity. Okay, so if you accept this, what you see is that this term here compensate exactly with this term, because indeed this was the definition of the point x naught. So there is no more y, and you get exactly that the first order term is minus dt phi at x naught, which is the formula I wrote here. If you remember that indeed the Legendre transform has the property that at the level of gradient, it gives the inverse. So the point x naught here is indeed grad psi t naught of z0. Okay, so when you have this, well, actually it's pretty straightforward, because you have an equation for dt for the evolution of dt, for the evolution of phi t, sorry, which I recall here. So you just plug this in the equation. So dt psi is now minus the Laplacian at the point grad psi of the Laplacian at point grad psi of phi, plus this term, so the gradient of phi at the point gradient psi. Okay, and now this, as I said, is grad psi is the inverse of grad phi, so this is just z square. And here, I recall that the Laplacian is just the trace of the Hessian. So you have the Hessian of phi at point grab psi, and again, the Hessian of phi at point grab psi is the inverse of the Legendre transform, of the Hessian of the Legendre transform. And this is exactly the formula. This is exactly the formula I claimed above. Okay. So let us go back to our question of proving that the monotony of the volume product. As I said, we want to compute. We want to check that this quantity is increasing. I'm taking the log. It's not really important and not really necessary, but it gives some homogeneity in the formulas. So I'm taking. I want to prove that this is increasing in time. Okay, where psi t is the Legendre transform of phi t. So of course now I have a formula, so I'm just computing the derivative in time. So this is minus dt psi of exponential minus phi divided by the integral. So again, this is, as before, I will just call it mu psi t, this probability measure. Okay, and now I write my formula. With a minus in front, I have the trace of the inverse of the Hessian of psi t minus y squared. Okay, and I want to prove that this is a non-negative, right? Now, of course, psi t here is exactly the potential of psi t of my measure. So it's somehow very tempting here to go back again to the Braskamp-Leib inequality. So here I recall the Braskamp-Leib inequality for my measure psi t. Okay, this is so except that instead of writing variance, I just wrote it in the case where u is center. So you have a function u that is center with respect to mu, and then the integral of u square is dominated by the inverse of the Hessian of psi t applied to grad u. So let me apply this inequality to the linear functions yi. So note that in my functional Blaschke-Santoro inequality, I am assuming that phi is even. So this is preserved by heat semi-group, and this is preserved by Legendre transform. So this function here, since psi t is even, my function is indeed centered. My linear functions are indeed centered. So I have that the integral of y square is dominated by this Hessian. And now what is the gradient? Well, the gradient is just, if I call EI the canonical orthonormal basis, this is EI dot EI, the gradient of my linear function. And when I sum all these functions, all these inequalities, I exactly find that the norm of y square, the integral of the norm of y square, is dominated by the trace of this Hessian. And this is exactly what I needed to prove that the derivative in time is positive. So this finishes the proof of the Blaschke-Santalo inequality with the use of the Braskamp-Leib inequality. So at this stage, it's interesting to note that I somehow use two times, right, the Braskamp-Leib inequality. I use it to prove that log concavity is preserved. When you do this, you really compute a second derivative, right, in time to check convexity. So here it's a bit different. Here I use it only for the first derivative in time. I prove that it's increasing. But I use it not only for one function, but for n functions. So somehow I'm using it for a vector. So okay, I think there is something behind it, but I have not cannot say more for the moment on this. But this is somehow for me it's a bit striking. Okay, so if you look at the argument, actually what we are proving is a bit more. We are proving that the Gaussians are the only possible maximizer, and actually the only possible even local maximizers. Why is that? But well, if you have some function phi that gives you a local maximizer, it means that when it evolves a long time, locally, it say in L1, it cannot increase, so it has to remain constant locally. And in particular, some derivative, so the derivative has to vanish. And I don't take the derivative at 0 because here I don't want to assume regularity. But of course, at t0/2, the function phi t is already regular. And so the derivative of my function alpha has to be 0. So this means that I must have equality in the Braskamp-Leib inequality. And the cases of equality in the Braskamp-Leib inequality, they are well known. These are just the span of the partial derivative of psi, right? So here I want the linear function to be equality cases. I am applying it to n linear functions, but these linear functions are independent. And so, of course, they have to span this space. So this means that every partial derivative of psi has to be a linear combination of the linear function. So this implies that the Hessian of psi is constant. So if you want, this tells you that the function psi t0 and the function, sorry, phi t0/2, they are both quadratic functions. And so this tells you that exponential minus phi t 0/2 is a center Gaussian. So this was just p t0/2 exponential minus phi has to be a center Gaussian. This is what the analysis of the equality cases in the Braskamp-Leib inequality gives you. But of course, well, the Hitsumi group is itself Gaussian, so there are many characterizations of when convolution of two things are Gaussian. But here it's pretty simple because just if you use, say, the injectivity of the Fourier transform in L1, this will tell you that indeed exponential minus phi has to be a center Gaussian. So these are the only equality cases. So I'm not assuming regularity, but somehow, as I told you, for the computations to make sense, what I did before, I'm assuming some superlinearity. And I would be very happy to get rid of this, but yeah, for the moment, it seems like a useful technical assumption. Okay, so I have some time to discuss a bit what happens in the non-even case. So what I will talk about is based on another joint work, another work with Mathieu Fradelesi and Dylan Langhorst. So in this paper, we really work with the Laplace transform, not with the Legendre transform, but you can somehow adapt the ideas we have in this paper, and I will tell you what it gives. So the first thing is that, of course, the Santalo inequality cannot hold if you don't assume anything, because there is this particular role of 0. For instance, if the origin is not in your convex set, just by the Hahn-Banach, you can separate it with a half space. And of course, you will have a full half space in the polar, right? So you must make some kind of assumptions. Just having 0 in the interior is not enough, because as I say here, you can make the volume tend to infinity by just translating your convex set. So nevertheless, there is a very well-known result that if you take the infimum over translations in the volume product, then indeed it holds that this is again maximized by the Euclidean ball. And you have the same result for the functional version. So if I call TZG the translator for the function G, again, if I take the infimum, so of course here it's invariant on the translation, but here I translate I translate phi, and then I take the Legendre transform. And then this is again maximized by Gaussians. And this was observed by Ashton, Clark-Tak, and Milman using the geometric inequality. So we would like to have a semi-group proof of this result. So again, what I need to check now is that when I look at the infimum in space of overall translation of the same integral as before, but here I have translations now, tz phi t, I would like to prove that this increases in time, okay? Because when, say, if you take Fokker-Planck, then phi t will tend to the quadratic, and then if phi t is just quadratic, and actually if phi t is even, it's easy to check that this infimum is indeed attained when z is equal to 0. So it will give you again the fact that the Gaussian are maximizable. So if you look the action, how translation act on the Legendre transform, well, you see that it gives you the Legendre transform plus a linear correction. So the function I'm looking at is the infimum over z of exponential minus the Legendre transform of phi t, that I call again psi t, times exponential z dot y. So this is just the infimum of the Laplace transform of exponential minus psi t. Okay, so I call L the Laplace transform. And I want to prove that this is increasing. Okay, so here, let me introduce the function q t of z. Again, I take the log. The log is not really important here. You can forget about it. So this is just the Laplace transform of exponential minus psi t. By the way, do you see the top of the, or not? I was wondering because I have this, okay, maybe.
I can see your pointer.
Okay, very good.
Yep.
Yes, so qtz is the log of the Laplace transform of exponential minus ct at point z. Here I recall the definition. And so the function I want to look at is, well, it was log of alpha, which is the infimum. I want to really look at the infimum over all z of this function qtz. And you have I think a rather nice property, which is a bit like Hamilton-Jacobi inequality, is that the derivative in time of q plus the gradient in space of q to the square of the norm is non-negative. So let me give you very quickly the argument. You more or less do the same thing as before. So you have this log of this integral, you compute the derivative. So you compute the derivative and you use the formula for the derivative of psi t, so the trace Hessian of psi t minus 1 minus y squared. And now the measure is slightly different because you have the exponential minus psi t, but then you have also a linear function in y, this dot y. But the point is that precisely this is a linear correction, so it will not change, for instance, the Hessian. So this is the Hessian of psi t, but it's also the Hessian of v of my potential. So I can again apply the Braskamp-Leib inequality, but this time what I don't have is that the linear functions are centered. So I have to work with the variance. And now you will use a property of the Laplace transform, because when you apply to the linear functions and you have a variance term, so you have the integral of y squared, and you will have the integral of yi of the square of this integral. But you see, since q is given by a Laplace transform, this barycenter is exactly the derivative with respect to the ith coordinate of q. And so what you get when you apply the Braskamp-Leib inequality is exactly this inequality. Okay, so what I want to prove is that the infimum is increasing. So I don't get anymore that this is non-negative. You see, I don't get that q is non-negative, because is q plus this positive term that is non-negative. But now, since I'm looking at since I am looking at the infimum, let me call ZT the point Z where this Q attains its minimum, right? Q is by the way, Q is a convex function. I should have mentioned it. Q by Hölder's inequality. Q is a convex function in space Z. So if you call ZT the minimum, so the formula is, okay, here are the formula is that the derivative of this log, the derivative of time of log Q, what is it? Well, you have, this is the derivative of time of Q. So I have the derivative with respect to the parameter T at the point ZT. And then I have also the derivative here in space of ZT, dtz, this is a vector field, okay, times the gradient in space of Q. But, and now I use my equation above. I say, okay, the derivative in time is greater than minus the gradient square. So I have this, this inequality. But by construction, I'm looking at the minimum. Okay, so the gradient in space at ZT is 0. So both terms are 0. And I get again that, that this is non-negative. So this proves the non-even case. And so in the last 3 minutes, I would like just to comment a bit, a bit more about this, because our result with Mathieu and Dylan was really about the Laplace transform in place of the Legendre transform. So this was a bit like in the Nakamura and Tsuji work that I mentioned. They proved some result in the even case for the Laplace transform and deduced the result for the Legendre. So what we did is to extend to the non-even case the result of Nakamura and Tsuji. And this, I mentioned here one kind of result that you can prove for the Laplace transform. So it's really the regime is for P below 1. So P is between 0 and 1, Q is its conjugate, so it's negative. And what you have is that for what you want to prove is this kind of inequality. So you want to prove that if F is in LP, its Laplace transform is in LQ. And this is like an improvement in the positivity because, of course, here Q is negative. So it somehow controls the fact that LF is far from being 0. So if F is even, Nakamura and Tsuji proved this inequality. And what we prove is that if you take indeed the supremum over all translation, you have the same result. So you have an inequality like this. The LP norm of the Laplace transform is above the LQ norm is above the LP norm with some constant for which there is equality. This is a sharp inequality, and there is equality for Gaussian functions. And you can remove this supremum if you assume, for instance, that f to the power p has barycenter at 0. Then you have this this inequality for any for the non-negative function. Okay, so I think my time is up. I will stop here. Thank you very much for your attention.
Okay, so let me first stop recording.